University, Sendai, Japan. The drone beam with primary energy of 10 kV bombarded the titanium D2 target. The low energy of primary neutrons allows to get the diffusion products with minimum deviation in their energy. The CR39 detector was placed at a distance near 4 cm from interaction point. Then the detector was etched and the tracks were investigated by microscope. In this microphotograph you can see tracks of 3 types of particles produced after the etching. Then, in this picture, you can see the distribution of number of tracks versus their diameters. There are 3 spikes on this distribution. According to the dependence of track diameter from ionization losses of particle, the higher ionization losses, the larger diameter, it is possible to suppose that the peak in the region near 5 microns corresponds to protons with energy 3 MeV. The peak in region 6.4 microns corresponds to tritons with energy 1 MeV, and the peak in the region 7.2 micron with long tail up to 10 micron corresponds to helium-3 nuclei with energy less than 0.8 MeV. Thus, we can see that these 3 types of DD reaction products can be detected and identified by CR39 technique. This we also need to note that this is the case of very thin layer of interaction for DD reaction. If we have thick sample, the track diameters may be intersected with each other, and it's very difficult to estimate the yield of DD reaction from thick samples. To investigate the CR39 response to helium-4 nuclei, the detector was irradiated by alpha particles from plutonium-239 and radium-226 sources through different aluminum floats. You can see the distribution of track diameters versus alpha particle energy for this measurement. The estimation of DD reaction yield by alpha particle measurement is very difficult because as I note, the alpha particle from DD reaction outgoing from thick sample will have energies from 0 to 3.5 MeV, and it is very difficult to measure different track diameters. DT neutrons also interact with CR39 detectors and produced very different tracks. We exposed our detectors by DT neutron source of Rare Metal Industry Institute in Moscow, Russia. The deuteron beam with energy 340 keV bombarded the titanium T2 target. We use both usual CR39 detectors and detectors with 60 micron polyethylene radiator. The detectors were placed at a distance near 31 centimeters from the target, and the fluence of DT neutrons at the detectors was near 2 on 10 to 8 neutrons per square centimeter. One of the DT neutron interaction in CR39 detector is the inelastic scattering of neutron on C20 nuclei caused the decay of this nuclei into 3 alpha particles. This detector has a cross section near 190 millibar at the neutron energy 14.5 MeV, and the detection threshold the DT neutron by this reaction in CR39 detector is near 10 MeV. And this transparency, you can see the different 3 alpha events when 3 alpha tracks are going from single point, and thus we can easily to detect this interaction of DT neutron with CR39 material and to detect DT neutron by this reaction. We estimate the mean detection efficiency for DT neutron by this reaction as 4.7 plus minus 0.6 on 10 into minus 7 for detector without radiator, and 1.2 plus minus 0.1 on 10 to minus 6 for CR39 with 60 microns of polyethylene radiator. The increasing of detection efficiency can be explained that DT neutron interact not only with CR39 carbon, but also with carbon in radiator layer. According to this calibration measurement, we try to estimate DT reaction yields in DT and DT reaction yields in different experiments. In this transparency, I present the results of measurement of DT reaction yields in deuterated palladium-palladium-O guitar structures. The samples of these guitar structures, like palladium oxide, palladium oxide samples were prepared in the Institute of Physical Chemistry, Russian Academy of Science, in Dr. Lipson group. From different palladium foils by vacuum annealing, palladium oxide layer was prepared by annealing in oxygen. The layer of aurum was produced by from electrolyte. These samples deuterated by electrolysis in one normal sodium hydroxide solution with current density near 20 milliamperes per square centimeter. The time of electrolysis was between 5 and 20 minutes. We can to estimate the deterioration yield from the samples only for a very thin boundary layer, less than 0.5 microns, because this is a 6 sample and deterioration products outgoing from 6 sample may have very different energy loss. To estimate the deterioration yields, we use the same procedure. According to calibration measurement, we try to count the double tracks. When the track with diameter near 5 micron is near the second track with diameter between 6 to 7.5 micron. The first track is attributed as proton track, and the second as tritium or helium-3 track. This coincidence of two tracks may be the coincidence not in time but in space. This coincidence may be accidental or give us the information that on this sample exist some zones with high concentration of deuterium atoms where a diffusion reaction is more probable. As we know, the critical angle of registration of proton, tritium and helium-3 with corresponding energies, we can to estimate the detection efficiency of this 3 type of particle as 0.13 for proton, for 3 MeV proton, 0.36 for 1 MeV tritium, 0.91 for helium-3 with energy 0.8 MeV. And to estimate the detection efficiency of this double coincidence we used the hydrogenated samples as a background in background measurement, and in this experiment we have foreground to background ratio near to 6. According to this calibration, we estimate the deterioration yield as from 2 to 6 on 10 to -3 per second into 4p solid angle per 1 square centimeter of sample. The measurement with the same samples carried out by silicon surface barrier detector gives the value 3.6 plus minus 1 on 10 to -3 into 4p solid angle. The deterioration yield was also estimated in the experiment in glow discharge of D2. These results will be presented in the poster number 044. 25. This also Karol believes Narusetsky. Tomorrow. Briefly, I can say that we used different cassettes like palladium, titanium, neodymium at the voltage of low discharge near 1.25 kilovolts. The 39 track detectors placed at different distance and protected by different absorbers to prevent ultraviolet irradiation of detectors from low discharge area. We estimate the direction yield in this experiment as value from 0.03 to 0.18 per second into 4p per square centimeter of cassette. According to calibration measurement, we also estimate the deterioration yield in deuterated palladium oxide gate structures. It was count near 30 square centimeters of detectors both in background and in foreground measurement. They look for events with serial particle tracks directed to single points, like serial events. In this picture you can see microphotographs of this picture is loaded. You can see these serial events from palladium oxide deuterated gate structures. In this case, the foreground to background ratio was near 4, and the mean flux of DT neutrons was estimated as less than 1 DT neutron per second per square centimeter of detector. To explain this DT reaction yield, we need to suppose that in the palladium oxide deuterated sample produced the fast returns with flux near 10 to 2 from 10 to 2 to 10 to 5 returns per second per square centimeter of sample. This return with energy from few kV to few MeV to explain this deterioration yield. There are at least two explanations of this effect. First one, the emission of DT neutrons as a result of production of fast returns by a known channel, or the second, the emission of high energy neutrons with energy more than 10 MeV resulted from some unknown nuclear reaction in this deuterated sample. I came to conclusion. First point, SER39 detector can be used in long-time cold fusion experiments, and it is possible to detect all DD and DT reaction products with characteristic response to every type of one. Second point, the results obtained with SER39 detector for the diffusion yield in palladium oxide hydrogenated sample are in good agreement with silicon surface barrier detector data. As the SER39 detector is insensible to gamma rays and electromagnetic noise, it can be used in low discharge experiments. This is the final point. Professor Tasagi for the help in the calibration of search-to-demand detectors. Thank you for attention.
Questions? Yes. Professor Casimos.
You said there are very high energy neutrons, above 10 million electron volts. And in such a case, how did you decide the neutron measured around few million electron volts produced by DD reaction? Because in the experiment by Lerici group in Italy, they measured also 2.45 million electron volt neutrons, and also more higher energy neutrons. And we analyzed by our model, it is possible to produce above 10 MeV neutrons if we consider reactions assisted by neutron. So I think your experiment is very similar to the results of Torino group. How did you confirm the low energy neutron is produced by DD reaction?
I think to reconfirm this measurement, we need to use some another measurement by different detectors, by different neutron detectors, and if we reconfirm this effect by different detectors, it's really truly DD neutron emission or some other high energy neutron emission.
Not so much a question as an observation. This would be a good detector to use to look at the Mizuni and Mori cell, because the electromagnetic noise there is fearsome. This would be a good device to use.
Didn't you refer to your poster? Wasn't that similar? Aren't you doing something similar to that in your poster? You talked about a glow discharge.
The poster about glow discharge experiment will be presented tomorrow by Dr. Barabut.
I guess it was different but similar.
Could you summarize the time when you used the deuterated solids? How long after they were deuterated did you do the measurement? And have you repeated the measurement again after you made the first one?
In this experiment, we use long-term exposition of detectors with deuterated samples and with hydrogenated samples to the time of the exposition, maybe few hours, and then this detector can be exposed again and again, and the information about particle tracks summarized in this detector, and after etching we can see the summary picture of this interaction.
I wonder about the decay rate of the source. The intensity of the particle rate must increase. If you repeat the measurement time after time, the source rate must be going down. Can you give us a decay time for the source?
Maybe, but this technique cannot estimate the time decay of the process. We only see some summary sample of this experiment. To separate the time is more difficult by this method.
Are there any more questions? All right, well, I guess we'll close the session. Of course, we have the dinner at 7:30 p.m., right? When are the buses leaving? Are they? Yeah, it's going to be here, but These shuttle buses, right? Yeah, okay.
I don't know which one yeah, right. Big crowd.
This room will be filled up soon. And I mean, not so many people are going out for testing. And I think it's time to start.
The ones who are here are going to nod off.
For chairman. I don't know. We have to start because of the schedule. And so this morning session, we have coffee break. We have 3 presentations. And first talk is done by Dr. Paper number 92. So you can see the abstract. And the title is the simple model of the Kern analog effect in peculiar electronic configuration of the experience.
Good morning. No, I ask you, forgive me.
You can just hold it.
Okay. Can you hear me?
Sure.
You have to turn it on.
I could.
Some experiment.
No, it's working.
It's working. It should work. You can hold it. You can hold it. It'll work.
It was working.
It was working.
Can you hear me?
Now you turned it off.
Push out. What?
Okay. Okay, good morning. I will speak today about a problem whose practical application is just a way of increasing the loading capability of the system. But this method has something to do with the structure of the palladium-hydrogen system. So it has an interest in itself as a contribution to the knowledge of the structure of the palladium-hydrogen system in the gamma phase. By the way, this title was submitted to this conference when Professor Preparata, which is the main author of these concepts, was still alive. Now that, unfortunately, he has passed, we propose from now on to call this effect after his name and to call it Preparata effect. My talk is organized as follows. I will describe, in the light of the concept of the theory of condensed matter, very briefly, how is the structure of the beta and gamma phase in a hydrogen palladium system. After, I will try to show that in the gamma phase, hydrogen atoms are in a coherent state, and which are the experimental consequences, the observable consequences, how this statement can be checked and observed. In the first section, I will show how this coherence affects the property of the loading. And in the last section, we will show by experimental check how these statements are true, in which sense are true, and verify this. In this sense, in this talk, I will give for the first time the experimental evidence of the existence of a gamma phase and of the coherence of hydrogen in this gamma phase. This independently of the existence of a phenomenon such as cold fusion, which of course is built up over this property. Now, it's well known that the hydrogen dissolved in a palladium matrix can exist in three phases. An alpha phase where hydrogens are spread around the matrix as the atoms of a gas, where the stoichiometric ratio X has very low value, and we are not interested now in this phase. In the beta phase, at room temperature, the stoichiometric ratio could be increased up about 2/3. In the beta phase, the atoms are quite localized in a specific position, the octahedral position in the lattice. And at this value of X, there is a transition. I will show now the nature of this transition. And we pass in the gamma phase, where on the contrary, hydrogens shift from the octahedral position to the tetrahedral position, and instead of being strictly localized, they are able to make wide oscillation around their equilibrium position, and this wide oscillation could be just the basis for the startup of the coherence. Here we can see which are the tetrahedral position, which are the octahedral position, because the palladium crystallizes into an FCC system, and the octahedral position are at midpoint of the sides of the parallelogram, and instead the tetrahedral position are at the midpoint of the nearest neighbor palladia. Some suspicion of the existence of a transition at X equal to 2/3 at room temperature can be observed in these graphs. Here, this graph is just the behavior with X of the diffusion coefficient of hydrogen into palladium. And this other graph is just the behavior of the unit lattice volume as a function of the loading. You can see that the palladium lattice grows quite a lot in the beta phase, and instead the increase is smaller in the gamma phase. Of course, the existence of such discontinuity could give a suspicion, not a proof, a suspicion that a phase transition could occur. In order to show if there is really a phase transition, starting from the approach of Giuliano to the quid coherence in matter, we've done an extensive calculation. Namely, starting from the coherence of the electrons in the palladium, it's possible to see that the d electrons in the palladium atoms are able to do plasma oscillation altogether, which met the coherence condition. So in this way, we have a plasma of coherent d electrons. We could have also a plasma of coherent s electrons. And just the two coherences originate, the first one, the beta phase, the other one, the gamma phase. According to this property, it's possible to calculate the profile of the potential generated by the electrons, in which the hydrogen nuclei see when they enter into the lattice. So, which environment the hydrogen atom found when they enter. And they found in the octahedral side a profile of the potential like that. You can see that the depth of this potential value is quite large. A well so deep cannot be obtained in any way from the conventional solid state consideration. Of course, no phonon dynamics could produce a well deep as much as 40 electron volts. But the existence of such well is necessary in order to understand, as Alfred Kuhn has discovered, why hydrogen get ionized when entering into the lattice. So the existence of such wells should be accepted necessarily, otherwise Alfred would have been wrong. In the tetrahedral sites, we have this different kind of wells, very narrower and deeper. So compare the two kinds of wells. In the octahedral side, the potential is like that, and in the tetrahedral side, like that. According to this distribution of the potential, it's possible to evaluate the chemical potential for both phases, namely the chemical potential for hydrogens which occupy the octahedral sites and the chemical potential for hydrogens occupying the tetrahedral sites. So the solid line is the beta phase, and you can see that this curve has a minimum just at a value which is near to the upper limit of the gamma phase. The chemical potential of the gamma phase is the dotted line, and you can see that the crossing of the two curves occurs just where a beta gamma transition could occur. So in this way we can show that here at x about 2/3 the chemical potential of the gamma phase crosses the curve of the chemical potential of the beta phase. Another observation is the calculation of the energy of the hydrogen nuclei while in this phase. And you can see the solid line show, as usual, the beta phase, the dotted line, the gamma phase. And you can see that the energy of the hydrogens in the gamma phase is quite higher. What that means? That means that in the formation of the beta phase is an exothermal reaction. The formation of the gamma phase is an endothermal reaction. That means that hydrogens, while in the beta phase, are located deeply into the well, while in the gamma phase they are located just on the upper part of the well. So they are less bound in the gamma phase than in the beta phase. And that's allowed the hydrogens, which are just in the upper part, to have wider oscillation. They are on the brink of the freedom, in a sense, in these wells. So in that case, the plasma of all the hydrogen nuclei approaches a sort of the ideal plasma. Is not far from the approximation of the ideal plasma. So this oscillation can meet quite more easily than the oscillation in the beta phase the coherence requirement and get tuned among them. Many years ago, in '72, Martin Fleischmann and his student Dan Dapani actually characterized the region of the phase space where there is an high loading of hydrogen as filled by hydrogens able to perform wide oscillation being into a large region. And this oscillation actually, when are able to tune among them, provide a coherent plasma. So, these graphs show that a phase transition could occur. Now the problem is that true or not? It's possible to check experimentally this statement. In order to check this statement, we could refer to a basic property of quantum physics. I will not describe here in detail. I will give only the consequence of this property. The property is the famous Böhm-Aronoff effect, who has been formulated in the late 50s by David Bohm and Yakir Aronoff, and consists in that a system, a particle, but also an ensemble of particles, described by a unique wave function, that is a wave function whose phase is defined. So the system has a defined phase. In this case, this system could detect and apply the potential. And this is a result which doesn't exist, of course, in classical physics, where potential can be revealed only through their mathematical function, which are the fields. In quantum physics, it's possible to detect directly the potential. Actually, because the potential through the Schrödinger equation enter into the phase of the wave function. So by measuring the phase, you measure the potential. And the consequence is that the potential adds up to the chemical potential of the system. Of course, when you have a piece of macroscopic matter, if this piece of macroscopic matter is described not by a unique wave function, but by a density matrix of wave function, namely by a mixture of wave function, each one referring to a single particle, but the relative phase of these different wave functions are uncertain. In that case, the phase average to zero, and this effect cannot be observed. But if you are able to fix the phases, and that's occur in a coherent state, you can observe a Böhm-Aronoff phenomenon. So the observation of a Böhm-Aronoff phenomenon will mean that the system you are observing is a coherent system. And this is the experimental proof of the existence of this coherence. Giuliano coined jokingly the word Ken-Aronoff, meaning that the system, the effect is similar to the well-known textbook Böhm-Aronoff effect. And since in this case the system is made up of charges according to Alfred Kane, which sounds like Böhm, so after Böhm-Aronoff we are Ken-Aronoff. Okay, now the joke is ended, and this is the Brevard effect. So, the criterion for observing this phenomenon should be the following. We have a piece of palladium filled up by hydrogen, supposedly in the gamma phase. Now we apply an electric potential to this system. Should the system be coherent, then its chemical potential should acquire an extra term, which is the applied potential times the electron charge times the screening factor. Because, of course, in this condition, the charge of hydrogen could be screened by the surrounding electrons. And by the way, this is an experimental means to check what is this screening factor. The importance of this property for the loading is that if you apply a negative potential, you can decrease the chemical potential into the metal, while the chemical potential outside remains constant. So in this way, you favor the tables for the loading, because loading becomes easier. In a sense, instead of increasing the kinetic energy of the impinging deuterons, instead of pushing them more strongly in order to put them, you decrease the height of the floor. Namely, you put the barrier which prevents the hydrogens from entering into the palladium, you depress this barrier, and the entering becomes easier. So the importance for the loading is evident. Of course, suppose that this is true. So what we have to show, that when there is an electric potential, the loading becomes higher. That's basically the effect. Now, you can, of course, tell me just instantly that When you apply an electric potential to a metal, you get a current, of course. The Ohm's law is true. And the current, through the Joule effect, heat the material and spoil the coherence. How can we manage through this puzzle? The solution is to have a very large internal resistance. If I apply a potential to a conductor which has a very high resistance, in that case the current becomes minimal. How we can do that? By not using massive cathodes or two-dimensional cathodes, but by using one-dimensional cathodes. If I have supposedly a wire, and this wire is very thin, has a very low cross-section, is very long, in that case the resistance of this wire is very high, I can apply a potential, getting a very tiny current. So the disturbance is minimal, and the advantage of having a potential is maximum. So this is the reason why, some years ago, we have shifted to a one-dimensional cathode, and we have neglected altogether massive cathodes and also plates, because we want to catch the good result of the Chenaronov preparata effect. So, and what is the check? We have made a comparison. We have made two cells. This is, of course, I'm not describing the real experiment. This is the task of Antonella, was already done. I'm describing, because I'm a theoretician, a sort of Gedanken experiment. We take two cells equal, with equal electrolyte, we apply the same electrolytic regime, and we use two different cathodes. In one cell we have a plate, in the other cell we have a deposition, a one-dimensional deposition in a boustrophedic configuration, like the line excavated by an ox who is just dragging a plough. And what we get? We get the, sorry, just a minute, because there is some disorder in my transparency. We have the following graph. First graph, the plate. The red line is the density of current, and the black line, the blue line, is just the ratio R over R dot, who, as you say very well, is the indication of the loading. And we can see that when we apply current, the system is loaded, and when we remove the current, the system discharges. What that means? That the system has been loaded only to the beta phase, because we are on the left side of the Baranovsky curve. I will show you now the Baranovsky curve. Because when we remove the current, the system discharges. The top of R over R naught is much lower than in the Baranovsky, the peak, than in the Baranovsky original curve, because of a phenomenon I will describe you in a while. Now, let's take now the deposition. Same regime. We don't apply an external potential because we use just the ohmic fall of the cell potential along the current. So we don't apply an extra potential. So this ohmic fall is enough to produce this this change. You can see that now when we apply the current, R over R naught decreases. When we remove the current, increases. And vice versa. What that means? That now we are on the right side of the Baranovsky curve, namely in the descending branch of the curve. Namely, with the same regime, we have increased the loading because in the first case, the system has settled in a situation where X was in the beta phase. And in the second case, the system has settled at much higher value of X. Now, I will skip some, because we have analyzed now this curve, which are R over R naught as a function of t. The existing curve are R over R naught as a function of X. So we must introduce into this experimental curve a theoretical curve, X as a function of t. And we have done this, but I have no time now to show you the detail. We have done that, and we have shown that the gain we have got is delta x about 0.3. Instead of loading at the value 0.6, the system has loaded at the value 0.9. This corresponds, in the curve of the chemical potential I have shown to you, to a change of chemical potential of 0.3 electron volt. Since the ohmic fall, namely the applied potential, was about 2 volts, that means that in the beta phase, the screening factor of the charge is slightly more than 0.1. Namely, that means that in the gamma phase, the hydrogen charge is heavily screened by the surrounding electrons. And that could help, of course, in the depression of the Coulomb barrier, which prevent the function. So all these results here, just in the end. That means that all the elements of the puzzle are fitting together because we realize that the system provides an advantage for people which are willing to fuse. The charge is effectively in this tetrahedral site heavily screened. At the end of this talk, I will show you a reason why in the plate the system loads at a lower value than in the Baranovsky peaks. And the problem is related to the existence of defects into the lattice structure. We have analyzed our material and we have found, forgive me if I don't show you the transparency, because now you can see that here there is a mess. I will lose a lot of time in extracting. Believe me on the word. In the proceeding, all the graphs will appear into the appropriate order. We have found that in the material which has been, in the cathode, which has been obtained by deposition, there are defects which are parallel to the surface of the deposition, and whose average distance is about 200 angstroms. This distance should be compared to the sides of the coherence domain of the electrons, which at full extension are just double as a diameter. So the existence of this defect produces a compression on the volume available for the build-up of the coherence domain. Now, the coherence domain have a size which depends on temperature, usually. Namely, they decrease, they shrink with temperature. Why? Because the thermal assault of the environment extract components from the coherent family and put some components of the coherence domain out of the phase. Okay. So the system decreases in volume. This mechanical bound on the sides of the coherence domain, in this sense, works as an increase of temperature. And in this case, the existence of this defect corresponds to a sort of a phenomenological shift of temperature. So the system behaves as it were at a higher temperature. And we know that the peak of the Baranovsky curve decreases with temperature. There is a very inspiring paper made 12 years ago and published in the Journal of Applied Physics. I will give you the reference to the interested people, where is shown just this dependence of the peak on the temperature. And according to this data, is it where, in our case, there will be a change of temperature of about 100 degrees. So the observed depression of R over R naught can be traced back to this phenomenon. So we can this fact, namely the depression of the peak, has been observed by many people in many materials. This shows how to understand this dependence of the peak on the metallurgy of the specimen. So in this case, the fact that in our experiment R over R naught didn't saturate the Baranovsky peak could be traced back to the stated existence of these defects. As a last statement, and after I will end my talk, I would say also that we are, and this topic will be shown this afternoon in the poster, to observe by using the synchrotron light the transition between the beta and gamma phase, shown by synchrotron light the shift of nuclei from the octahedral to the tetrahedral position, and this should be a pictorial view of this transition, which now we have proved electrolytically. Thank you.
I have to make one or two points. I agree with the idea of coherence. I mean, first thing, the H plasma mode is nothing but phonon modes. Hydrogen plasma mode is nothing but phonon modes. So the coherence comes in the coherence of phonon modes. Over and above this story, we should think of what is called the charge order states of these hydrogen materials. And over and above that, there can be charge density wave, which is more effective for the processes.
No, okay, I agree with you. If you are able to find out a phonon dynamics able to build up coherence, of course, but unfortunately, the conventional solid-state physics doesn't do that.
No, what I mean,
okay. No, I want only to stress that this phenomenon cannot be told into the usual books because they don't have a coherent build-up of the interaction, so deep wells cannot be exhibited. And you need this well, otherwise hydrogen should not be ionized. So the ionization, the Kane effect is as much troublemaking for the conventional physics as the cold fusion is itself. So this story of the gas-metal system is a story of miracles, in a sense, because people should explain why hydrogens are ionized.
There's a literature, a very large literature on palladium hydride that goes back over 50 years. And this literature shows that the region between pure palladium and 0.6, or where you call the end of the beta phase, is actually a two-phase region, consisting of the alpha and beta, right? So that region, the properties of that region are a physical average of the two end members, and the activity is constant. It's normally not called a single phase, it's a two-phase mixture. And on the other hand, the beta phase, which everybody else in the world calls a beta phase and you call a gamma phase, is a octahedral compound. Neutron diffraction studies of this up to about 0.9 show that there is no tetrahedral occupancy. So my question is, how do you reconcile your statements and your model to these facts?
The situation, of course, I simplified. The word simplified is also in the title because of the short time available. A more refined version, I have anticipated in discussing the depression of the peak, is that hydrogen are both in a coherent and in non-coherent situation, because since temperature is not the absolute zero, of course the thermal assaults, the thermal fluctuation, extract particles from the coherent picture. So as in water in the old-fashioned Röntgen model, there is a coherent part which is described by this function, and a non-coherent part which behaves in a sense as the alpha phase, which is a gas, a non-coherent fraction. By increasing temperature, the non-coherent part acquires importance at the expense of the coherent part. So there is a maximum temperature where coherence disappears altogether, and this explains the critical factor. The existence of defect, as I have shown, for instance, confines the coherent region to a smaller extent than in the absence of this, and this affects the R over R naught ratio. Of course, a way is opened to a detailed consideration of all these phenomena if we are able, for each temperature, to calculate what is the coherent fraction. We have not yet done that, but we have a program to do that. It's not a very simple problem from a mathematical point of view, but it's doable. So I hope that. Now I have concentrated on the coherent, only on the coherent fraction in order to show the novelty we are acquiring.
There is something that Ed said that I don't think you realize. And what he was saying, he said the neutron diffraction. And it is quite true that the neutron diffraction indicates that there's an alpha-beta mixed phase and a beta phase. But the point is that when you are dealing with the neutron diffraction studies that he's referring to, which is what a lot of conventional solid-state physicists do, you're really dealing with an ordered configuration that's pretty much three-dimensional. And it's best characterized at really fairly low temperatures, like below 60 degrees Kelvin. Now, in a one-dimensional configuration that you're talking about, it is not forbidden, for example, from local density theory calculations that you would get the tetrahedral occupation. But I think there's a more important point, which is to try to get the language straight. Ed is right about, part of the problem with a lot of the things that you guys have been doing is the language. And you got to try to fit it into what people use.
No, I agree. Yes, I agree that the language is a problem.
It is, because people won't accept it.
In that way, in order to clarify the language, one should separate the word ordered and the word coherent. You an ordered system which is not coherent.
Order does exhibit coherence at low enough temperature. And the phonons that he's talking about is another way of talking about it. It's talking about the same thing in different ways.
No, the problem is coherence means that you can define a phase.
And you can.
But if you have a system with a definite number of particles, according to quantum field theory, you cannot. Because there is an uncertainty principle, like the Heisenberg one, who said that the uncertainty in the number of the particle times the uncertainty in the phase should be larger than the Planck constant.
Yeah, but
so, forgive me. In this way, in order to have coherence, you need an oscillation between two states. In only one state, you cannot have coherence. You have order, of course, particles distributing in an ordered way. But they don't oscillate.
Okay. Now, so I'm sorry, I'll stop now. We'll discuss right now during the time of the first session. So, discuss our questions. Let's speak on
and the language.
The title is Research for Coherent Neutron Fusion by Beam and Electronics Experiment.
The title is Search for Coherent Neutron Fusion by Beam and Electrolysis Experiment. I'd like to introduce two types of experiments, namely closed-time PDB electrolysis experiment, and electron beam stimulation experiment, and ion beam experiment. To begin first, I show the closed-time PGD electrolysis experiment. Measurement of neutron excess heat and deloading ratio
performed during the electrolysis. And after the electrolysis, helium-4 detection was tried for the upper cell gas, and since there is possibility that generated helium-4 was accumulated in the palladium cathode, so the electrolyzed cathode was heated up after the electrolysis, and released gas was also analyzed. This figure shows the schematic view of the experimental setup. Neutron detection was performed with NV213 disintegration detector or helium-3 gas detector. Heat measurement was performed using mass flow calorimetry method. This figure shows the cross-sectional view of the electrolysis cell. The coolant pipe was set in the cell wall, and heat recovery efficiency is about 95%. And the cell was sealed with this copper gasket, and internal gas was isolated from the overside gas. And this upper cell gas was analyzed after the electrolysis. This figure shows the mass analysis system. Sampling gas was sent to this analysis part through this line. This is a suction pump for collecting D2 or N2 gas. By using this suction pump, the resolution of this mass analysis system is very improved. I showed the example. The upper figure is a mass spectrum measured without throwback pump, and the lower is measured with a suction pump. In the upper figure, these gas peaks overlaps on the helium gas peaks, but by using the suction pump, these gas was removed. Then helium-4 peaks so read clearly. And after the electrolysis, the electrode cathode was set on the heater in the vacuum chamber, then evacuated the chamber, and then the sample was heated up to 350 centigrades, and released gas was sent to the analysis chamber. I show the summary of the experimental results. Totally, we performed the 3 runs, and palladium cathode used in this experiment was treated as like this, annealing or metal coating. In the 3 out of 7 rounds, we can detect the helium-4. Especially in XP4, we can detect the helium-4 so clearly. I show the results of EXP4. The upper figure shows mass spectra for upper cell gas in EXP4, and the lower is the released gas by heating the electrolyzed palladium cathode. Before electrolysis, 1.1 times 10 to 15th atoms of helium-4 was detected in the upper cell gas, and after the electrolysis, 4.7 times 16th atoms of helium-4 was detected. Therefore, 4.6 times 10 to 60th atoms of helium-4 was generated during the electrolysis. And this amount cannot be explained by the contamination, because we need much amount of air leakage to explain this value. And also in the released gas, we can detect the 8.1 times 10 to 60th atoms of helium-4. Considering that before the heating of the cathode, we cannot detect the helium-4, so this helium-4 must be released from the cathode. And we also detect the helium-4 in ESP2 and ESP3. I show the results. These are mass spectrum of the ESP2 and ESP3. This is helium-4 peak. And next I show the results of the neutron detection in the ESP2 and ESP3. We can detect the meaningful increase of the neutron counts in this experiment. So therefore, we can detect the correlation between helium-4 generation and neutron emission in this experiment. And in the EXP3, we can detect a very slight amount of heat generation, 2 watts for 60 watts input. And the heat generation was continued about 130 hours. This is a short summary of this experiment. Significant amount of helium-4 atoms were detected in 3 out of 7 lamps. In one of them, increase of helium-4 4.6 times 10 to 60 atoms were detected in upper cell gas. In the released gas by heating up the electrolyte cathode, 8.1 times 60 atoms of helium-4 were detected. Slight amount of excess heat was detected in one of the lamps. Correlation between helium-4 generation and neutron emission was not detected. Next, I show the electron beam stimulation experiments. This experiment is a trial to induce the multibody fusion by stimulating PDDX or TIDX with electron beam. Measurements of charged particles, X-rays, and gamma rays and low energy X-rays were performed during the electron beam irradiation. This figure shows the schematic view of the experimental setup. The detectors were attached to the chamber like this, and the electron gun was here. The beam energy is about 3 keV, and the current is about 3 microampere. And the beam diameter is about 1 millimeter on target. Two identical SSBDs were set symmetrically to the electron beam, and 2 identical cadmium telluride X-ray detectors were set like this. And we used PDDX or TIDX as a target in this experiment, and TIDX were prepared by using a gas loading method, and PDDX were prepared by using the electrolysis rolling method. And after the electrolysis, the palladium deuteride was coated with thin copper layer by electroplating method to prevent trapped deuterium releasing out. I show the data. This is measured by cadmium telluride 1 and cadmium telluride 2, and SSBD1, SSBD2. The energy spectrum measured by SSBDs were similar to the background, but in the energy spectrum of the cadmium telluride detectors, we can recognize here the bumps from 10 kV to 20 kV. And so the target was palladium deuteride. So I compare the spectrum with background spectrum. Figure in the upper side foreground and in the lower side background. In the region from 10 kV to 20 kV, count per second in foreground line is 20 times as large as of background in case of cadmium telluride 1. It's similar in the case of cadmium telluride 2. The count was also increased above 20 kV And since electron beam energy was about 3 keV, energy of X-rays by slowing down of the incident electron must not exceed 3 keV. And considering that the similar spectra were detected by 2 identical detectors, these spectra cannot be explained by detector's malfunction. And because the energy spectra by SSBDs were same to the ordinary background, these signals may not be electromagnetic noise. Therefore, there is every possibility that these spectra are due to a tail of a Compton continuum or continuous X-rays by slowing down of charged particles. But of course, to confirm this assumption, further experiments are necessary. Short summary of this experiment. Measurements of charged particle X-rays and gamma rays are performed under electron beam radiation to highly deloaded metals. Anomalous continuous spectra, which were obviously different from of background, were detected by 2 identical cadmium telluride detectors in the one using PDDX as a target. Next, I show the ion beam experiment. To detect coherently induced deuteron fusion, measurements of charged particles were performed under ion beam radiation to highly deloaded TIDX. In addition, the origin of the particles were investigated by following measurements. Experiments of particle identification with delta E and E counter telescope, and measurements of the variation of emitted charged particles kinetic energy by changing the detection angle to the incident beam, and measurement of the variation of the yields of charged particles by changing incident beam energy. This figure shows the setup of experimental chamber for G-beam implantation. Conventional SSBD were set here. This detector were used for the total energy measurement of the charged particles. And the E and the delta E counter telescope were set here. The sample was set on this cooling device. The beam energy was changed from 50 kV to 300 kV, and the beam current was about 20 microampere on target. And we call this detector EK detector. This is the energy spectrum measured with the EK detector, and we could recognize here and here anomalous shoulder. This shoulder is obviously different from the pileup curve. This dotted line shows the calculated pileup curve. And to investigate these shoulders, we performed the experiment using the delta E and E counter telescope. The upper figure shows that the upper figure is measured with delta E detector, and the lower is E detector. And this particle maybe this shoulder lost its own energy in the E detector. So we consider that this particle is helium-3. And helium-3, considering their stopping power in silicon. And the other shoulder, this shoulder is concluded to be a triton in the same way. And from these results, the shoulders were recognized to be responses of helium-3 and of triton respectively. Therefore, we conceive that the origin of this shoulder is this 3D reactions. But considering the energy loss values of each particle before hitting to the Lerici detector, the 3D reaction should take place at deeper place in target, about 3 micron to 5 micron depth. Since beam scanning range is about 2 micron for 300 kV deuteron, the reaction was induced at the end of the beam scanning range or more deeper place. And in addition, this figure shows the variation of the ratio of the helium-3 is over DD reactions. This ratio shows the tendency to increase at lower beam energy. In general, beam target interactions at low energy, reaction cross-section decreases more than DD reaction as incident beam energy decreases. But as shown in this figure, the detected reaction cross-section increase at lower energy comparing with the DD reaction. Therefore, the detected 3D fusion is not direct interaction with the incident deuteron, but maybe indirect reactions and a coherent effect in far less energy than the beam. Here we can imagine so-called cold fusion. And to confirm that the 3D reaction is an indirect reaction, we perform the experiment using proton beam and proton beam instead of deuteron beam. If our assumption previously mentioned is true, we could detect the 3D reaction also in the experiments using proton beam and TIDX. The setup is similar to the deuteron beam experiment, but this is a detector for high energy charged particles measurement. So screen foil of nickel 600 micron was set in front of the detectors. And we call this detector EH detector. This is the energy spectrum measured with an EK detector, and we can recognize here the anomalous counts. And we cannot explain these counts by looking into these impurity reactions. So we make assumption. This 3D reaction will take place in the deeper place in the target, and emitted triton have about 4.3 MeV at the detector. This value agrees with this peak very well. And partner particle of helium-3 have about 3.3 MeV at detector, so the responses of helium-3 was helium-3 may hide in this continuant. And this explanation is consistent with the discussion for the deuteron beam results of the deuteron beam experiment. Therefore, the incident beam play a role only for generating the condition in which the multibody D reactions are induced. In other words, multibody deuteron reactions are not a direct beam target interactions. And next I show the energy spectrum measured with the EH detector. we can recognize here several counts, and these signals are supposed to be responsive of protons by the HDD reaction, because any other considerable emitted charged particle cannot penetrate through the 6-screen foil set in front of the detector, considering their stopping power. And considerable mechanism to induce this HDD reaction is like this. First, under the stimulation by ion beam irradiation, two deuterons approach each other closely, and DD pairs are produced transitionally. And thus, incident proton hits to induce HDD reactions. From these experimental results of ion beam experiment, in the surface region of the target, so-called subdirect interaction was take place. First, DD pairs were produced, then an incident deuteron or protons hits to induce DD reaction or HDD reactions. And at deeper place in the target, indirect interaction of 3D reaction were induced. Summary of ion beam experiment. The responses which suggested the occurrence of the 3D reaction were detected in both deuteron and proton beam experiment. The detected 3D reaction is not a direct interaction with the incident beam, but maybe indirect reactions and a coherent effect in far less energy than the incident beam. At the surface of the target, subdirect DDD or HDD reactions may be induced as a result of the incident particle hits to DD pairs. DD pairs were produced transitionally by lattice dynamics. At last, I make discussion of these experimental results. The results of the three kinds of experiments could be summarized as follows. Significant amount of helium-4 atoms were detected in electrolysis experiments where neutron emissions were not detected. And low-energy continuous responses were detected in the experiments using low-energy electron beam and palladium deuteride. And the responses which suggested the occurrence of 3D reaction were detected in the ion beam experiments. So we conceive that multi-body reaction, 3D or 4D, are of key importance to explain the experimental results. The outgoing channel of 3D and 4D reaction can be drawn as like this. The detected charged particles in ion beam experiments may be produced by the reaction 2. But this outgoing channel 2 is supposed to be a minor channel, considering the spin parity selection rules. The vertical compound nucleus of lithium-6 star may have hot parity, so it should transit by even photon emissions to lower even parity state. Therefore, considerable main channels are 1, 5, and 6. Results of the electrolysis experiment as helium-4 generation with neutron emission can be explained by the reaction 1, 5, or 6. There is a possibility that the detected signals and electron beam irradiation were Bremsstrahlung X-rays by slowing down of those charged particles by 1 or 6. I conclude this presentation as follows. The results detected in the three kinds of experiments can be explained by multi-body reaction model consistently. Multi-body reaction may be induced under lattice coherent motion in transitional process as suggested in the results of the ion beam experiments. To search how these conditions can be realized much more strongly and to work out how 3D over 4D cluster can be made are important tasks in the future. Thank you very much.
In one of your transparencies, you said that you could measure gamma rays. Could I ask you, did you measure any gamma rays between 1 and 24 MeV?
In experimental electron video.
You said you could measure gamma rays in one.
But in this round, we cannot measure gamma rays because after this experiment, we start to measure gamma rays. So we have no data of gamma rays in this experiment.
But you will have data later. You will have data on gamma rays later.
No.
But you said in your transparency you could measure X-rays and gamma rays.
Yes, but we cannot detect gamma rays in this lab.
Did not.
I have 2 or 3 questions. First one is for the electron beam measurement. What kind of background did you measure? You said the background measurement. Did you bombard the palladium with a deuteron? I mean, not without deuteron.
Yes. And we performed the background experiment by using pure palladium, not deloaded.
And then you didn't see any X-ray, you said, for the background lab?
Yes.
Okay. And then for the ion beam measurement, it is, for me, your data does not convince me because your particle identification, I'm a little bit suspicious about that because you said that one thing is in the pilot region, and you just draw the background of pilot from the calculation. It is very dangerous, seems to me. And maybe you should measure the pilots because the pilot shape is very much depending on the various parameters, for example, the time constant of amplifier and so on. So you should be careful. And then the other thing is, why I'm saying that is, I did the same experiment and I didn't see any helium-3 or T. And I was using very thin delta E detectors. But we could clearly separate, we could clearly identify the particles, alpha particle and proton, but no helium-3 and triton in that region. And also, what we saw is the sequential reactions, DD going to the helium-3 plus N, and helium-3 interact with deuteron and makes an alpha particle and neutrons, something like that. And then, if in that level, we couldn't see any helium-3 or triton emission from the target. That's why I'm asking.
Maybe I can answer as one collaborator shortly. We have done the pilot measurement also, and we didn't see such a fine shape for usual pilot. We have experimental data for the advancing, and for others, we are using the different samples from US for titanium deuterium. So the station would be different.
I wanted to get clear. The tritons in the 3D reaction in the TIDX, what you observed, were they at 4.75 MeV? 4.75 million electron volts they were. Well, it's interesting. Just a thought. I don't know if it has bearing. You know, George Chambers, Graham Hubler, and those guys, a decade ago, were looking at the TIDX films, and you probably thought of them. The energies, of course, their incident beams were considerably lower in value. I think the energies of the tritons were right around the same. So it may be very useful to think about as further justification of the three-body interaction.
Dr. Pojin.
Questions on the electrolysis experiment. I want to know the size and the electrolyte experiment. Perhaps I missed.
Size of electrode?
Yes.
About 25 millimeter, and 1 millimeter thickness.
Then, your experiment shows helium-4 detected is in the gas is with a similar amount in the cathode. In my memory, many experiments made in these 10 years shows many helium-4 in gas and few in electrode. One is done by Mallove and Bush, and it is perhaps 3% helium-4 is in cathode. And in the case of pond electrodes, it's also showed, analyzed in 6 laboratories in the United States. The helium-4 in cathode is very low. They didn't measure in the gas. In your case, the helium-4 in gas and the helium-4 in cathode is comparable. And how do you think about the reason of these values? Perhaps it have very strong relation with the result Mike McCauley presented first day. And second question is helium-3, did you measure in the electrolyte experiment? 2 questions, please.
For the first question, and heated temperature is about 360 centigrade. It's very low temperature, so the detected helium-4 was accumulated in the surface of the very surface of the cathode, maybe. So all of the surface helium-4 was released to the gas part of the cell. We can detect the much amount of helium-4 in the gas side of the cell. And the next question is tritium. Helium-3. We cannot detect the helium-3 and we cannot measure the helium-3 in this experiment.
Measured, but no helium-3.
No, not measured.
Not measured.
Yes.
Okay, any other question? If not, thank you.
Thank you very much.
Now I shall call the first speaker in this morning session, your coffee break, Luca Mengoni. Number paper 7. That is anomalous effect induced by electrolysis at
ladies and gentlemen, can you hear me? No. Thank you. The paper which I am going to present deals with the discharge of heavy water after titanium cathodes to induce, if possible, anomalous effects. So we had to address some questions. The first one is it possible to achieve titanium hydrate through the electrolysis from a liquid water titanium environment? Here I am presenting a Courbet graph, which is well known to the electrochemists. And this graph was drawn at the beginning of the 60s and accounts for the stability range of several species of titanium in function of the potential applied and the pH. And I am not able to see in any place the stability range of titanium hydride. Now, about 40 years after this plot, if I should put the stability range of titanium hydride, I would be very puzzled. Because indeed, titanium hydride is not easily achieved through water discharge in aqueous medium. There are some reports about the production of titanium hydride through water discharge in acidic medium. As instead concerns the discharge of alkaline electrolytes, I can show this result from a review of Mizuno and Degno, which show the squares. What was the amount of hydrogen extracted after electrolysis in this pH range at titanium? The experiment was performed by galvanostatic charging with a rather low current, 10 milliamps, and was lasting about 1 day or something less. And you see that for pH at about 9, practically no hydrogen was absorbed. Anyway, if you are going back to the Courbet diagram, we see that for very large, very small current applied, we have, when we are already in the discharge of water, we probably are in the titanium oxide range, which is quite impervious to hydrogen absorption. Here, in fact, I am reproducing the current potential curves obtained at titanium at pH of about 11. And we see that with 10 milliamps amperes applied, more or less here, the potential is probably at around -1 volt or below against normal hydrogen electron. Even with currents with about 300 milliamperes per square centimeter, which is a large current, the potential of the free surface of titanium cannot anyway be achieved. So, the situation is rather discouraging with respect to titanium hydride formation from alkaline electrolyte. Anyway, the report by Mizuno was, which is not surely to be questioned, was not considering other facts, the nature of the sample and the temperature. In fact, the diffusion coefficient of hydrogen in titanium is very low, at about 10⁻12 at room temperature, but it can be increased over near 2 magnitude orders if we are working near 100 degrees. On examining several types of titanium samples, we tried to detect if hydrogen was inserted into the sample by a rather simple but significant test at the end of the electrolysis. The sample was polarized galvanostatic for over 24 hours with 100 milliamperes applied, and then, after opening the circuit, the potential transit was recorded. According to this procedure, we could divide in 3 groups the several samples. One group, we will name group 1, the interruption of the circuit was followed by a fast transient decay, and practically the electrode was achieving the potential of titanium dioxide phases. At the opposite side, with other batch of titanium, we observed a slow increase in transient at 25 degrees. And the same experiment performed at 95 degrees was showing a still more slow transient, which is amplified in this side. We see here that the potential had a fluctuation and oscillation. We can interpret this behavior as the decomposition of bulk hydride phases through this corrosion reaction. And the potential which we are measuring clearly is a mixed potential controlled by the occurrence of this reaction. The slow transient observed at 95 degrees fits with the hypothesis that the amount of hydrogen loaded at that temperature was higher than the amount obtained loaded at 25 degrees. So, we have investigated by a calorimetric technique working at 95 degrees, which we have already presented at ASTI, the titanium heavy water system at 95 degrees using sample 2 type electrodes. The calorimetric system consists of a thermostatic bath in which we have the dual cell. The dual cell contains a heater, both the electrode, a pipe, and is equipped with a refrigerating column. When the system is at 95 degrees, owing to the evaporation, the cell is not reaching, the temperature inside the cell is not the same of that of the bath. So I have to supply continuously some power to the heater
to make the cell isothermal with the calorimetric bath. I have the problem of the stirring, which is solved by a controlled draft of nitrogen entering the cell. This must be rigorously controlled because most of the heat loss takes place through the column, and clearly the gas is increasing the evaporation. The function of the gas, other than distributing the heat inside the cell, is also to eliminate the oxygen and the hydrogen produced during electrolysis. This way, you can also avoid the question, if you are achieving heat effects, what about internal recombination? Well, the samples which were giving behavior 1, that is immediately decaying potential transient, were giving no thermal effect. With the sample of 2 types, this one, which had the dimension of about 5, a surface of about between 5 and 6 square centimeters. We started the electrolysis with a very low current, about 65 milliamperes. The continuous curve represents the temperature of the cell. The dotted curve represents the joule power entering the cell. Dotted and broken curve represent the total power fed to the cell. Through the PT100 thermometer, the temperature is read with accuracy better than 0.05 degrees. And through calibration, we can convert this temperature in power. The accuracy of power determination in this case is lower than the accuracy of temperature because of considering linear the temperature in this range. Clearly, 0 point means 95 degrees, and this temperature increment is above 95 degrees. Anyway, we were increasing the current, and the phenomenon was well increasing, and then declining steadily. We were assured in excess power. At this point, about 1 day later, we were increasing the current to about 250 milliamperes. And after 2,800 minutes since the beginning of the electrolysis, about 2 days, since we observed the trend to a steep increase in the temperature, we went obsessive, and we were observing this phenomenon. The temperature was increasing, reaching a maximum, and after that it was not relaxing according to the thermal heat loss of the cell. After more than 1 day, we applied again current. (55 milliamps). and the temperature was steadily decreasing. We were increasing the current, and the decrease was not stopped. So we arrived at about the level of the Joule effect here. At this point, we increased again 0.25 amperes, and we went to open circuit. We had again a thermal effect, but the relaxation time this time could be put in comparison with the characteristics of the cell. Eventually, current was applied for the last time, 250 milliamperes for 3 days. And when observing again an increase, we went to open circuit. We observed a still more significant after effect, or heat after death, or heat in the absence of any external supply. It is interesting to note that the effect could be quenched by very small current applied. In some way, the applied current either confines the effect or it quenches it at all. Anyway, going again to open circuit, the phenomenon was lasting about a week. And here I have the shape of the phenomenon. This effect could be reproduced with other samples. Of the same batch. Here we were relating to the first hour of the after effect. This is the experiment which I have described before, and this are experiment with thinner samples. I have also to say that with this same batch of titanium, the effect was observed also with light water. Since the corrosion reaction, which I have shown before, surely are exothermal reaction, the only thing which we could do was to take the weight of the electrode before and after the experiment. And indeed, what we observed was only a small weight increase at below 1%, which could be accounted for instance, also by hydrogen absorbed by the system. But clearly, the fact that thermal effects were obtained with both light water and heavy water is rather puzzling about the nature of the process. So, we were observing just the sample utilized in light water with a germanium detector. And it was impossible to see anything due to the background. So we devised this type of detector. A detector working in coincidence. That is, the sample is put here and is seen by 2 high resolution germanium detectors. After that, we have that the constant fraction discrimination is controlling the gate energy of the system, and the amplitude controller are controlling the coincidence of the system. In other words, at the detector, only the signal which are above an energy threshold and coincident within less than half microsecond can be revealed. Clearly, this system implies that each detector was previously carefully calibrated with the background lines of thorium, lead, and polonium. These lines are no longer available when the system is working in coincidence. The first sample we were observing was the sample prepared in light water, and the reaction we were looking for was this one. That is the formation of an unstable vanadium-4, which eventually decays with 2 gamma rays to titanium-47, and the result was negative. So we move again to heavy water, and the reaction considered in this case was this one, titanium-48, which reacts with deuterium to produce an intermediate state of then scandium-46, which is beta minus unstable, and we produce both helium-4 and scandium-46, which is beta unstable and decays to titanium, which relax to the ground state with the emission of 2 gammas. The scheme of the decay can be found on the table, and this more or less this one. In other words, we have a gamma of 889 GeV, and again the